Hi everyone! In this video, I'm going to discuss how to get a transfer function of a MIMO system by block reduction method, in which MIMO stands for multi-input and multi-output. Before we dig into the problem, let's review the basic rules for block diagram reduction. When two or more blocks are connected one after another, meaning the output of one block is the input of the next, they are said to be in series. To reduce a series connection, we simply multiply the transfer functions of the blocks. So here we have G1 and G2 are series together, then the transfer function will be G1 times G2. And this rule can be applied to any number of blocks connected in series. Just multiply them together in the order they appear. For parallel systems, if they are in parallel, summation will do. When two or more blocks receive the same input and their outputs are combined at a summing point, they are considered to be a parallel. To reduce a parallel connection, we simply add or subtract the transfer function depending on the sign at the summing junction. So here, if we have G1 and G2 connected in parallel with positive signs, then the equivalent transfer function will be G1 plus G2. And if one of them is subtracted at the summing point, then it will be G1 minus G2. Here in the second case, if we have like a short line, we don't have any block in here, then it will be represented by 1. It will be G1 plus 1. For feedback systems, we have two types of feedback systems, a negative feedback loop and positive feedback loop. First, let's say what's the difference between a forward path and feedback path. G of S here is a forward path, which have an input and getting an output already. But a feedback path is branching from an output signal to returning to a summing point. Okay, if we have the feedback loop connected to a summing point with a positive sign, then the transfer function will be G of S over 1 minus G of S, H of S. But if we have the feedback path connected to the summing point with a negative sign, then it will be G of S over 1 plus G of S times H of S. Okay, for a displacement of summing point, if a summing point is before a block and you want to move it after, multiply the branch entering summation point by the transfer function by the block. And if a summation point is after a block and you want to move it before the block, divide the branch entering the summation by the block. Displacement of feedback point is just the opposite of displacement of a summing point. If the feedback point is before a block and you move it after, divide the feedback path by G of S. And if the feedback point is after a block and you want to move it before, multiply the feedback path by the block. And now let's start with the example that we want to discuss it after we review the basic rules of block reduction. Okay, in this example we have two inputs, R1 and R2, and two outputs, C1 and C2. So we need to get four transfer functions, which are C1 over R1, C1 of S over R2 of S, C2 of S over R1 of S, and C2 of S over R2 of S. So let's start with finding the first transfer function C1 of S over R1 of S using the superposition method. This means we focus only on the path from R1 to C1 while temporarily removing R2 and C2. An important point to note: when a block connects to a summing junction, as shown here, its signs matters. So here G2 is originally enters the summing point with a negative sign. Then once R2 is removed, G2 should be considered as negative G2, not positive G2, as shown here. So we neglected R2 and C2 and we got the negative sign to G2. So let's start arranging the block diagram to start block diagram reduction. Okay, for arranging, first we have G1 is proportional to the output C1. Then we're having a feedback loop consisting of G2, negative G2, don't forget the negative sign, in series with G4 and G3. Then negative G2, which is in series with G3 and G4, feeds back into this summing point located before G1. Okay, here is the final block diagram after arrangement. This is what the block diagram looks. Now let's start with reducing this block diagram. We have negative G2, G4, and G3 are in series, so they could be reduced by multiplying them together. This creates a direct feedback loop with the transfer function G1. Okay, as a result, the reduced block diagram will give a transfer function as G1 over 1 minus G3 times G4 times G2. And this is the final transfer function we have for C1 over R1. Then repeat the same steps for the other transfer functions. I will not dive into them in this video to keep it short, but I will go through them so you could follow along, and if you have any questions you could leave them in the comments and I will reply shortly. Thanks for watching. If you found this video helpful, please give it a like and consider subscribing to the channel for more content like that. Here is the transfer function of C1 of S over R2 of S. And this is C2 of S over R1 of S. And this is C2 of S over R2 of S. Thank you for watching.